Welcome to these lectures on algebraic geometry and commutative algebra. Recall that in the last lecture I have introduced Noetherian and Artinian modules, and today we will see their properties and some statements about submodules, quotient modules, etc. Main fundamental observation we will use from the last lecture is that a Noetherian ordered set, an ordered set is Noetherian if and only if the opposite ordered set is Artinian. So, let us start formally. So, as usual I will write A as given base ring, and all our rings are commutative, that I will not say often, and V for a module V is an A module. We have associated an ordered set submodules of set of submodules of V with a natural inclusion. This is an ordered set with natural inclusion, and we know V is Noetherian if and only if this ordered set is a Noetherian ordered set. So, let us prove a typical statement about submodules and quotient modules. So, that I will call that as a lemma. So, let U be a submodule of V, and V by U the residue class module of V by U. This is also, some people also call it, and I also call sometimes, quotient module. Okay, now the assertion will be, when V is Noetherian, is it true that U is Noetherian, is it true that V by U is Noetherian, and what about the converse. So proof the statement, then V is Noetherian respectively Artinian if and only if both U and V by W are Noetherian respectively Artinian. And just now, beginning remark, we only have to prove the assertion for Noetherian. We only need to prove the assertion for Noetherianness. I will just note here, because the set S A V, this inclusion is Noetherian if and only if the opposite one S A V op is Artinian. And obviously, if I take S A V this op and op of that, these are isomorphic. ordered sets. That means there is a bijective map between them which preserve the order. So, before I prove this formally, I will need some easy observation from the earlier courses like abstract algebra. So, I will recall. So, recall that two observations, one will be for rings and the other will be for modules. So, the first one, this is also known as correspondence theorem for rings. So, let A be a ring and A be an ideal, and assume that the Gothi K, which is an ideal, which is not the unit ideal. Now, we have this natural map, the canonical surjective ring homomorphism from A to A mod A. This is the residue class ring and this is I denote by pi. This usually I will denote by A going to A bar, where A bar is, I will not write this, but this is a coset of the small a modulo this Gothi case, so that is A plus A, but this is, I will not use this often. Okay. So, under this ring homomorphism, what happens to the ideals? That is because we have to ultimately study the ordered set of ideals. So, the relation between them is, so S A mod A, or I will use our earlier notation which I introduced, I of A mod A. These are all ideals in the ring A mod A. On the other side, we have ideals in the ring A. So, this contains a subset, all those ideals B in I A such that A is contained in B. Now, this correspondence theorem says that there is a bijection here, there exists a bijection and that bijection is inclusion preserving. Bijection. So, one should say there exists bijection which is inclusion preserving. That means, if you call this as alpha, this means if B is contained in B prime and both these belongs here, that means A is contained in them, then the image here alpha B is contained in alpha B prime, and similarly for the inverse. I will not write it. Similarly for the inverse alpha inverse of alpha. All right, actually one can give this bijection very easily. So, for example, where will B go? B will go to, so B is an ideal here which contains A. So, take its image under pi. So, B will go to pi of B. What is more important here is, more important comment is, because pi is surjective, this is an ideal in A by A, since pi is surjective. In general, image of an ideal is not an ideal in general. All right. And the inverse is what? If I have B bar ideal in the residue class ring A mod A, then you just take the inverse image of inverse image under pi inverse of B bar. This obviously will contain pi inverse of 0, because 0 belongs to the ideal B bar always. So, pi inverse of 0 bar to be strictly speaking, but this is nothing but the kernel of pi, and we have seen in earlier lecture this is precisely the given ideal A. So, these are obviously these are inverses of each other, and they by very definition they preserve the inclusion. So, this is what you have to prove. Formally it is bijective, but I leave that proof, you would have seen in earlier courses. All right. So, this is one, and more generally for models we can write such a statement which will also be used in the proof of the lemma. So, now if V is a module and U is a submodule, so this is the second observation. Before I want to give the title for that. This is called a correspondence theorem for modules. It describes the submodules of the quotient module and the original module. So, A ring, V A module, and U is a submodule, A submodule. Then we have defined this quotient module or residue class module V by U, where elements I will denote them as x bars, where x varies in V. So, x bar is x plus U, the coset of the subgroup, but again I will not use this very much, I will use the bars only. And more important is, we have a map, surjective map pi from V to V by U. This is surjective A module homomorphism. And this same analogy we are describing SA submodules of V by U, and here is we have SA V, obviously not all, but I will take a subset, and earlier observation tells you what subset to take. So, all V prime in which is a submodule of V which contain U, U is contained in V prime, and we want to give a map here, that is any V prime go to the image of pi of V prime, and this is a bijection and inclusion preserving. In fact, we can write the inverse with inverse any V bar going to pi inverse of V bar. These are easy to check. In fact, instead of saying bijection which preserves inclusion, one could also say that isomorphism of ordered sets. This is an ordered set, this is also ordered set, and these ordered sets are isomorphic. It has obvious meaning. So, this is what we will use in the proof of the lemma. So, let us start the proof. So, this is proof of lemma. First, I will prove this way, this implication. So, that means I am assume that V is Noetherian. Then what is the definition of Noetherian? Every non-empty family of submodules has a maximal element, and we want to check that U is Noetherian. But any non-empty family of submodules of U will also be a family of submodules of V, and therefore, it has a maximal element, and that is, so this is clear. So, I would just say clearly U is Noetherian. Now, the residue clause module also is the same, because we have a bijection between. So, we have here SAV, this is a Noetherian ordered set, and there is a subset of all those V prime such that U is contained in V prime, and this ordered set is isomorphic to this. That is what the observation 2 says, and this is Noetherian, and subordered set of a Noetherian is Noetherian. That is also clear, because the element if you have a subfamily here, subset here, non-empty, it has a maximal element, the same is a subset there, therefore, and therefore, this is Noetherian, and therefore, this is Noetherian, because isomorphic. Isomorphic as ordered set, that is very important. So, this way is very easy. Remember or note that this is very easy because our setup is very clear. So, now the conversely, so we are assuming U and V by U, suppose that both are Noetherian, are Noetherian, and to prove that V is Noetherian. Now, V is Noetherian means either, now I will use one of the lemma which I proved in earlier lecture. To prove somebody is Noetherian, I would prove that it satisfies ascending chain condition. So, suppose we need to prove that, we will prove that V has ACC. So, for this let V0 contained in V1 contained in Vn contained in Vn plus 1. This is a chain of submodules, ascending chain, in SAV. Then I want to prove that some stage is there from where it is equality. Now, How am I going to use U is Noetherian? Obviously intersect this whole chain with U. So we will get V0 intersection U contained in V1 intersection U and so on, Vn intersection U, Vn plus 1 intersection U. Now because U is Noetherian, this chain has to terminate somewhere. So I will choose N so that it's equality here. So choose N naught in N such that Vn naught intersection U equal to Vn intersection U for all n bigger equal to n naught. This I can choose because U is Noetherian. Now next what? Now I want to use the fact that the quotient module V by U is Noetherian. Since V by U is Noetherian, I claim that. So look at from the original chain, see we need to use this V by U is Noetherian, we need a chain in V by U, but right now we have only chain in V and all of them will not contain U. So to overcome this remedy, consider I will write a statement and then we will prove that. You look at that U V0 plus U, V0 plus U is clearly contained in V1 plus U because V0 is contained in V. So this Vn plus U contained in Vn plus 1 U and so on. Now I get a chain, this is an ascending chain of still submodules in V, but all these guys contain U and therefore I can apply I can pass on the chain to submodules in V by U and conclude that that is stationary because the bijection was inclusion preserving bijection between the submodules of V by U and submodules of V which contain U. We can conclude that this chain is stationary. That means there is a stage, so that is there exists, now I will call it N1 in N such that Vn1 plus U equal to Vn plus U for all n bigger equal to N1. But remember we have to go back. Now from here we want to conclude from which stage it becomes equal or the original chain. So therefore I will take the maximum of N0 and N1 and say that there exists M in N such that if I take Vn intersection U, that is Vm intersection U and Vn plus U equal to Vm plus U for all n bigger equal to M. I just take M equal to maximum and look at this and the earlier one. So now it is important here, now recall, I would need to recall this. So now from here I want to conclude that from this conclude that Vn equal to Vm for all n bigger equal to m by the following modular laws. Modular law. So, I will state that modular law and leave the proof for you to check. Okay. Modular law is also very simple. You probably would have studied in the first course on abstract algebra. So, what is the modular law? All right. So, this is the modular law. Modular law for submodules. So, V, I need lot of letters. So, V, U, W and N be A submodules of the module V of the A module V. So, let U, W, N, they are A submodules of the A module V with U is contained in W. There also we will have this situation. Then if I take W intersected with U intersection N, W intersection with U plus N, this is same thing as U plus W intersection N. See, this basically commutes the operation intersection and plus. This is very easy to check, and you apply this to the earlier situation and you will conclude V n equal to V m for all n bigger equal to m. So, this proves that. So, I should have said earlier here over here. So, once you from this you conclude that this, and hence, so this will prove, this will prove, this will prove that V is Noetherian, and that proves the lemma. All right. All right. So, now let us continue with the corollaries, consequences of this lemma. Corollary 1, let f from V to W be an A module homomorphism. Okay. Then V is Noetherian, respectively Artinian, if and only if both kernel of F and image of F, both are submodules of one is a submodule of V and the other is a submodule of W, are Noetherian, respectively Artinian. Again we will indicate the proof only in the Noetherian case. Artinian case will follow like similarly. Now what is the advantage here? Now since we would have seen in earlier lecture that V mod quotient module of V by the kernel F, this is isomorphic as A modules to image of F, which is a submodule of W. And what is this isomorphism? Actually one can write down the isomorphism very easily, namely x bar is mapped to f of x for any x in V. This you have to check it is well defined. So check this is well defined and bijective and so on. I will not check that, it is very easy to check. So you check that it is an isomorphism. One, this is an isomorphism. What is given to us? We have given image is Noetherian, that is this quotient module is Noetherian and this kernel is Noetherian. So therefore this corollary will be immediate from that. The next one, next corollary, so let 0 to V prime to F to V, F is homomorphism from V prime to V double prime to 0, be an exact, I will explain this, exact sequence of A modules, and strictly speaking I should write also and A module homomorphism. So what does this mean first? This means, so this is F prime and this is F here. So this means, so that is three things. Number one, this F prime is injective. See, whenever we talk about modules and the maps between the modules, we understand that they are A module homomorphisms. We do not talk about arbitrary maps between the modules. So F prime is injective. Second thing, the image of F prime equal to kernel of F. And third thing, F is surjective. These three things mean that such a sequence is a short exact sequence actually. Short also one should remember. I will write that in a bracket. So this injectivity is indicated by a 0 before and the arrow. That means the next map is injective. And surjectivity is indicated by the arrow and the 0 after that. That is indicated this 1 and 2. And here the kernel here equal to the image here, that is this condition 2. Okay, then what is the statement? Then V is Noetherian, the middle one respectively Artinian, if and only if V prime and V double prime are Noetherian respectively Artinian. Both. Proof. So what is the assumption meaning? Let us write down. So look at this map F prime is injective. So therefore V prime will be isomorphic to the image of F prime. Because this map is just any x prime goes to F prime of x prime. this is injective and I have only taken the elements in the image, therefore surjective, therefore this is isomorphism which is a submodule of V. And when you apply the quotient thing to this and V double prime, because this map is surjective, this is isomorphic to V by kernel F, quotient module kernel F, because this map, again the map is x bar going to f of x bar, f of x, and this is surjective, therefore this is an isomorphism. And but this kernel equal to image that is given to us. So, this is same as V modulo image of f prime. So, I have now this V prime is Noetherian, therefore this is Noetherian. So, this is, and V double prime is Noetherian, therefore this is Noetherian. So, I can apply the lemma. So, now apply lemma to conclude the proof. Alright, so that proves this is one way to check some module is Noetherian or not. These are, I am collecting the facts. How do you prove modules are Noetherian? By economical statements. Okay, so we will have a break and then continue in the later half. Thank you.